This is the video for Group C's Energy Lab done by Mark Moran, Matthew Sweeney, and PJ Wagener. Just to preview what this video will be, we'd like to say we decided to make the video through still pictures and voice recordings like this because the lab space was much too loud to produce a quality video, so we figured this would be better. So here we have the setup of our lab. We have our ramp wedged against the wall of the lab. We have our two objects to be rolled, one black cylinder and one 1 kilogram mass, and we have our motion sensor at the end of the track to pick up the object's velocity. Additionally, as a later shot will show, we tape 2 meter sticks to the ramp to form a sort of track for the objects to roll down through. So at this stage of the lab, several measurements were taken. We massed the 2 objects to be rolled, and we measured the height, length, and hypotenuse of the triangle formed by the ramp, table, and wall. The objects were massed so that we could determine both their initial potential energy and final kinetic energy, both of which help in examining the work done in the system. We measured the triangle dimensions so that we could determine both the angle of the ramp and the distance traveled by the objects, both also important to examining work done in the system. So here we have a simple diagram showing the setup of the lab. We have our ramp, the cylinder at the top of the ramp, the motion sensor at the bottom of the ramp, and we have the measured length and height, both horizontal and vertical respectively. And here we figure out the angle, which is 6.12 degrees, and that is found by a simple trig, inverse tangent of height over length. Here we have a look at the setup of the forces in this experiment. We have a simple free body diagram over on the left. You can see we have the weight acting straight down, the mg. We have the normal force acting perpendicular up from the plane of the ramp, and the static friction acting straight up the ramp in the opposite direction of the motion of the object. Then we have the sum of the forces. In the y direction, it is the normal force minus mg cosine theta due to the angle, which we found from trig in the last section to be 6.12 degrees. And in the x direction, it is mg sine theta minus the coefficient of friction times the normal force, which is mg cosine theta, by solving the EFY. And if you do some substitution and rearranging, you find that the coefficient of friction is equal to the quantity gravity sine theta minus the acceleration over gravity cosine theta. Now, we solved for the coefficient of friction because that is one way to differentiate between the experiment with the cylinder and the experiment with the mass, because they have different coefficients of friction between themselves and the ramp. However, we're not actually going to use this equation we found. We are going to find this coefficient using the energy way. So here we have the setup for the energy aspect of the lab. We have the Wien equation where delta K plus delta U plus work done by friction equals the work input. Some rearranging, you get kinetic initial plus potential initial equals kinetic final plus potential final plus work done by friction. Obviously, the kinetic initial and the potential final will go to 0, and doing some rearranging, you get a equation which solves for the coefficient of friction, US, or mu s, which equals gravity times the height initial minus the final velocity squared all over 2 times gravity times cosine theta times the distance of the ramp. Now we'll calculate coefficients for all the trials later, but using the values from the first trial with the cylinder, we find that the static coefficient is 0.0123, the red number there. Additionally, on the right, we have the delta K, delta U, and work done by friction. All are positive except the delta U. Obviously, the potential change is negative, and we find that the work in is actually equal to negative 0.330 in the first trial, which we will discuss later. Now, PJ will discuss the procedure of our lab.
So in this lab, we are looking to find kinetic energy. We're going to first start out by taking this mass and rolling it down the ramp. The velocity we measured on the iPad. So first putting it at the top of the ramp, we put the mass and we let it go. As it rolls down the ramp, it increases in kinetic energy. And we can find this increase in kinetic energy by measuring the velocity on the iPad.
This is our data from the iPad aspect of the lab. The first picture is from the cylinder, and the second is from the mass. The data we gathered from these graphs was the final velocity, which we found at the end of that diagonal line. Now, just a quick note on everyone participating in the video. I know Matthew Sweeney is not in this, but we had some technology problems on getting his voice into this, so I am doing his part, but the credit should go to him for the conclusion. Here we have the data spreadsheet for our lab. The data points highlighted in green are things that were kept constant throughout the experiment, except for the object being rolled, of course. And in blue, we have the data points we pulled off of the iPad graph, the final velocities for each trial. In pink, we have the calculations done, showing the transfers of energy. As you can see, the change in kinetic is positive and the change in potential is negative, because we went from positive potential to zero potential, and from zero kinetic to positive kinetic. We calculated the work done by friction using the coefficient calculated in the yellow, which we found using the equation shown in the energy setup. We assumed our work in would not be zero because it is a real-life experiment, and both values were negative, both for the cylinder and the 1 kilogram experiment, which we attributed to the rulers we lined on the ramp for the track for the rolling objects. As you can see, the values are negative, so therefore if we were able to add in the work done by the friction of the rulers on the track, they would have been a positive addition to the win equation, bringing it closer to zero. As you can see, the values remain consistent throughout the two experiments, showing either dark magic or that the outside forces were rather consistent. Some errors present in the lab include the friction loss to the rulers that made the track, some possible random imprecisions in the measuring, and our general inability to work the iPad app, SparkView. Our conclusion about the transfer of energy is that it starts as all potential energy and becomes kinetic energy, and there is work done by friction in between. Thank you for watching our video.